In this video, we'll talk about IT-OT convergence. This is the shift that changed the security posture of OT networks more than anything else in the past 2 decades. Understanding it is essential for understanding why the controls in this course, segmentation, firewalls, secure access, monitoring, are no longer optional features of a well-run facility. They're compensating for a fundamental change in the threat environment. Again, a lot of the things we've talked about, and we'll revisit them during this lecture. For most of the history of industrial control systems, OT networks were physically isolated from everything else. No connection to corporate IT, no connection to the internet, no remote access paths of any kind. Again, systems were air-gapped. There was a literal physical separation between networks. The air gap was the primary security protection. It wasn't designed as a security measure. It was the natural consequence of building systems before Ethernet was ubiquitous and before the business case for connectivity existed. But the effect was real. A control system that isn't connected to anything external is very difficult to attack remotely. Without a network path in, an attacker needs physical access to the facility. That air gap provided meaningful protection even for systems that had no other security measures. No authentication, no on PLCs, no encryption, no access controls. When the network can't be reached from outside, those gaps matter less. When the network can be reached, they matter enormously. The business case for connecting OT to IT networks is real and it continues to grow. Remote monitoring lets operators and managers view process data from a central location or from any device, enabling faster response to abnormal conditions across geographically distributed facilities. Vendor remote access lets equipment manufacturers diagnose problems without sending a technician on site, reducing downtime and cost significantly. Enterprise integration sends production data automatically to ERP systems, MES systems, and business analytics platforms. A plant manager can see current production rates, yields, and efficiency metrics in real time without waiting for a shift report. Cloud historians aggregate data across multiple sites, enabling advanced analytics and performance benchmarking. All of these provide operational and business value. They also eliminate the air gap and open network paths into environments that were designed with air gap as the implicit security model. The security assumptions that made air-gapped OT safe no longer apply once the gap is gone. OT equipment was designed for one thing: reliability in a controlled environment over a very long operational life. PLCs, RTUs, and DCS systems are expected to run for 15 to 30 years with minimal maintenance. Security was not a design requirement because in air-gapped environment it wasn't needed. The consequences of that design philosophy show up clearly when these devices are connected to a network. Most OT devices cannot be patched in the way IT devices can. There's no monthly patch cycle. There's no automatic update mechanism. A PLC firmware update requires a maintenance window, vendor coordination, and often recertification of the control application. For safety critical systems, the approval process is very extensive. The result is that many OT devices run firmware that's years or decades old with known vulnerabilities that have never been addressed. Many OT devices cannot run security software at all. There's no endpoint detection, no host-based firewall, no logging agent. The processor and memory are sized for control, not for security monitoring. Some OT devices fail or freeze when they receive unexpected network traffic. The TCP/IP stacks in these devices are minimal. They're designed for specific traffic they expected to receive, not for the variety of traffic on a connected network. Active port scanners, which are routine in IT security assessments, have caused PLCs to fault and stop executing their control programs in real OT environments. This isn't a fringe case. This is documented and has really happened in many CISA advisories. Standard IT security practices often cause operational problems when applied directly to OT. Aggressive vulnerability scanning, intrusive patch management, endpoint agents that consume processing overhead. These practices are designed for systems that can tolerate occasional disruption, OT systems often cannot. History explains why OT security is its own discipline rather than just applying IT security to industrial equipment. You can't patch your way to security in OT environments at the same pace as IT. You can't run endpoint agents on embedded controllers. You can't accept the operational risk of aggressive active scanning on production systems. The toolbox is different, the risk tolerance is different, and the consequences of getting it wrong are different. What you can do is control the network. You can segment the OT environment into zones that limit what can reach what. You can place firewalls at zone boundaries that enforce least connectivity. You can use passive monitoring tools that watch traffic without sending any. You can require VPN and multi-factor authentication for all remote access. You can eliminate plain text protocols from paths where they're no longer necessary. These network level controls don't require any changes to the OT devices themselves. They sit around the devices and compensate for the security limitations baked into equipment that was never designed for a connected environment. That's the philosophy behind the rest of this module and Module 5. In the next video, we'll introduce the Purdue model, which is the reference architecture that gives us a common framework for talking about OT network zone structure.